Hello, my name is Paisley Code. I am a master's student at Virginia Tech in Computer Science. I'm going to be discussing a paper in the energy harvesting field, and this sort of discusses a new method of writing programs for energy harvesting devices, or devices which use energy harvesting and use intermittent computing as well. So this is Alpaca, which is intermittent execution without checkpoints. This paper is written by Qiwan Meng, Alexei Collin, and Brandon Lucia. They're all from Carnegie Mellon University. Alpaca in this case stands for Adaptive Lightweight Programming Abstraction for Consistency and Atomicity. The two last features, consistency and atomicity, are two aspects which are really prioritized in this method. So first I will discuss some energy harvesting and intermittent computing background in order to introduce this paper. So first, there are a couple key features for energy harvesting devices, for intermittent computing devices. So this essentially needs to have computation only happen with environmental energy. So essentially, if there's no environmental energy, it's not able to function. However, one consequence with environmental energy is that it's not really consistent. It can disappear over time, and since there's no battery or constant power supply, such as a computer plugged into a wall socket or a laptop with a battery that's attached, it sort of needs to take in consideration that, okay, this device is going to lose power at any given moment. And it needs to come up with methods in order to preserve the past data functioning, or the past data and memory that it currently is using. And it also needs to come up with a method to ensure that no programming errors can come up when it's interrupted in the middle of it. So this environmental energy can be solar or radio or any other type of device, and the measuring method obviously changes depending on the type of energy that it's taking advantage of. So as you can see in this example, we have the environmental energy in the background, and then it's received by the energy storage, and it's received through various methods depending on the type of energy that's collecting. And then when enough energy is stored, it is then able to run a computation. For example, it could run encryption, or it could use a sensor, or honestly anything. And then once that computation is run and the power is used up, then it sort of needs to, the power is dissipated, demonstrated by this arrow going into the void, and then it needs to collect more environmental energy in order to run the computation again and continue performing the encryption or whatever operation it was performing in the first place. So next, we have certain requirements and goals for intermittent computing. So some requirements are preserving progress, volatile and non-volatile memory management, and respecting atomicity constraints. And these requirements are things which need to happen in order for the device to run correctly. If any of these properties are violated, then you'll either get an incorrect operation or no operation at all. So you'll either get an encryption that doesn't work, or it just won't get encrypted at all. For goals, these are aspects which are desirable, but can be sacrificed to ensure that the requirements are met. A lot of these goals are also very similar to regular computing goals as well. So the first requirement is to preserve progress. This is especially important since power is intermittent. So any progress on a long-term computation needs to be maintained. So for example, with the encryption, if you're halfway through the encryption and then you lose power, then you're going to need to restart that encryption from the start. So there are certain methods which are used to help preserve progress in these circumstances. One is a checkpoint system, which most of the prior work in this field already uses. So this essentially sort of takes a checkpoint and then continues after that checkpoint, and then until it takes another checkpoint. If the power runs out, it returns back to the same checkpoint, similar to other types of checkpoints in general. Next, we have volatile and non-volatile memory management. So this is sort of a complication introduced by taking checkpoints. So volatile memory is a type of memory storage which requires power, and the contents disappear when energy is not fed into it. So essentially, in the case of intermittent computing, if the power disappears, or the power goes out, or there's a lapse, or the energy is all used up, then the volatile memory is not stored and it cannot get back. And it's pretty unfortunate since we've lost all that precious information that we've already ran. It's just a huge drawback. However, it is also a lot faster than non-volatile memory management. So in this case, it can be sort of useful since it's able to run before it's run and perform an operation before the power runs out. So this can be very useful in this circumstance. Yes. And then there's also non-volatile memory management, which does not require power to be maintained and is a bit slower. And this can be useful since when the power runs out, it still preserves its progress and everything's great since that's still maintained. However, it can bring up a couple of issues. For example, if it's a bit slower and a little bit energy inefficient, then when the power may run out before the checkpoint's able to be taken, and it would be a little bit slower and not able to run as efficiently as it would otherwise. So both need to be synchronized to function as intended. So in this example, you can see sample code from RSA, a sample potential encryption algorithm used for this intermittent computing device. And we can see that we have non-volatile memory stored up here. So we have these arrays, and then we also have carry, which is going to be the variable which we're going to focus on in the next example. This example is provided in the paper Alpaca. And then we also have this checkpoint taken here, where we're essentially sort of taking a checkpoint. And then we also change the value of carry after the checkpoint, after performing this operation. So carry is sort of like changing its value. So when we look at this sample execution, we have carry being set to C, and then we're sort of taking a checkpoint afterwards, and then we're running the operation again with a different value for carry. So you can see here carry is being run in this version now, it's being run with this, and then carry is being set to a different value of C. And this is all being stored in non-volatile memory for this. So let's just say there's a power outage, power disappears, and then we need to continue back where we left off. So we load that checkpoint, but we still have the value of carry stored in non-volatile memory. So we sort of have the future, if you can consider it like that, the next iteration of carry being used in this function when we should be using the previous version of carry because the checkpoint was taken with that previous version. So we're sort of like running this operation with the incorrect value. And this can cause a lot of issues when we're considering encryption, since we're sort of using the incorrect encryption, and then when we try and decrypt it, it's not going to function as intended, and huge mess. This is essentially sort of not going to function well. So this is one potential consideration to take into account for intermittent computing. And it's also something that you need to be very careful of in order to manage volatile and non-volatile memory in the correct manner. Next, we're going to look at respecting atomicity constraints. So atomicity is an operation that is completed entirely or not at all. So in this case, it's sort of a way of thinking about a certain operation. So for example, an operation can be split into multiple steps, but when treated by the program, we sort of want to treat it as one whole step. And this can prevent memory issues, such as in this example right here. So for example, let's just say we have an intermittent computing device which takes the temperature in a certain location and then sends the temperature and the time to a server in order to update them on the current temperature in that location. So first we take the current time, and then let's just say we have a checkpoint in the execution, and then the power goes kaput, oh no, and then we sort of take the temperature after that point. Then when we send that temperature, it's going to be incorrect with the incorrect time. And if this is like a couple seconds difference, in this specific example, it might not be a huge deal. However, if the power disappears for a longer period of time, then the temperature and time matchup is going to be completely off. And then there's also going to be issues for other types of operations where it's sort of completed halfway. So in these cases, you want to take into consideration that certain operations need to be completed all at once, while some aren't. This is sort of the flip side of the preserving progress goal. You want to preserve progress in some circumstances, but there's some cases, such as with sensors, where you don't want to do that. So you sort of want to find a way to accommodate for both of these sort of different types of situations. So next up, we're going to look at some of the goals. So the first goal is flexibility across different hardware architectures. And this, as stated before, this is sort of a universal goal for any type of computing, but also important for intermittent computing as well. In this case, it can be hard to maintain consistency between different types of intermittent computing devices since they have different resources available to them. For example, you may have one intermittent computing device which exclusively uses non-volatile memory, and a solution developed for that one is going to look very different than one that uses volatile memory and non-volatile memory. Since in that situation, the volatile memory isn't necessarily going to be preserved in the solution for the first one. And this can help increase scalability since you're able to use these solutions across multiple different types of platforms and even future devices later on, and potentially also different types of power harvesting sources, energy harvesting sources as well. So it's good to sort of like keep that in mind, being able to have that flexibility. Next, we have behavior adjustments at different power levels. This is definitely one that's sort of exclusive or more in consideration for energy harvesting or in intermittent computing devices, since we may want different behavior adjustments at different power levels. For example, at a higher power level, that means you have more time to perform the operation before the power disappears, so you may want to perform a longer or an atomized computation at the start to maximize efficiency. Well, that's like one potential example. But the more common one is at a lower power level, you'd want to store the current state. So that way then you want to ensure that, okay, the current state is going to be stored, and then you don't necessarily need to do it concurrently. Sort of see, okay, the power is running out, I need to save my current progress before I continue, or else I will not be able to have that saved. So that's one potential consideration. And the final one is efficiency. So for efficiency, you sort of want to ensure that your system is efficient as possible. And this can be either due to memory management, storage, power, and all of these are going to be important for an intermittent computing device, especially for power, since you need to make sure that it runs in a timely fashion so that when the process can finish before the power runs out. And you also need to have something be more conservative with power consumption. Otherwise, then it's going to use up all the power and then not be able to perform the actual operation or other types of operations in that time. So in this example, you can see that there are a series of checkpoints being taken, and checkpoints are very useful for maintaining progress since you're able to sort of like not need to backtrack as stated before. However, in this case, it's going to be pretty inefficient and energy consuming and time consuming to constantly take checkpoints after each execution or line. So you sort of want to make sure that you're sort of taking those two things into account. You want to maintain progress, but you also want to make sure that your intermittent computing device can run as intended and perform the operation that it needs to. So as with most things, Alpaca does not exist in a vacuum, and there is some prior work which is associated and which Alpaca uses to influence some of its decisions. So first, there are prior examples of volatile checkpointing. There's also Chain, which is a paper written by Colin and Lucia, which they discuss intensively in this paper since it is also a task-based system, but uses a slightly different method of memory management. Next, there is Dino, which uses almost constant state saving or constant selective state saving in certain circumstances in order to help preserve memory when power fluctuations are really intense. So for instance, in cases of RF, the power sustainability can be very low. It can run out of power very quickly, and power is very inconsistent. So Dino in this case stands for death is not an option, since this program is going to keep running or keep being able to make progress consistently. Next, there's also Ratchet, which adds lightweight checkpoints for pre-existing programs with a focus on ease of use and being able to use it on programs which aren't necessarily created for intermittent computing. So you can take a program intended for something else or a computing device with a consistent power source and then still able to use it on an intermittent computing device with this method. And these are all methods which all provide multiple different pros and cons in certain circumstances. So as you can see here, there are some implementations in energy harvesting which can help mitigate some of the previous issues provided earlier and which some of the prior work uses. So these examples are volatile checkpointing, static and dynamic checkpoints, and task-based systems. And these all are different methods to sort of mitigate the issues mentioned earlier. So the first one is volatile checkpointing, and this helps ensure progress. but it does not necessarily ensure volatile and non-volatile state consistency if performed incorrectly. There are some cases where it will be able to perform correctly, which I'll go into later, but in order to help maintain progress and keep track of the volatile memory, you're going to need to take checkpoints consistently. And as you can see in this example, which I mentioned earlier, of RSA, this is an example of it sort of taking a checkpoint and having it not work out correctly. So this is a potential issue. However, one thing of note is that this is a right after read inconsistency. So a lot of the other solutions, such as I think Ratchet, Chain, and also Alpaca, they all take this into consideration and take extra care to keep an eye out for these inconsistencies and then take action to ensure that these inconsistencies are prevented throughout the program and when being compiled. Next, we have static and dynamic checkpoints. So these are used to Chain, Dyno, and Ratchet. These are essentially just methods of taking checkpoints of different aspects. So a static checkpoint essentially takes a checkpoint of the entire state, I believe, and a dynamic checkpoint sort of takes a checkpoint of a certain data value at that point in order to ensure that it's more consistent. So these sort of create copies of modified data, and these help ensure volatile and non-volatile state consistency. So instead of just storing volatile memory with no heed to the current state of some of the different variables in the program, it sort of ensures that these are kept consistent by taking carefully selected checkpoints. However, there are a couple of issues with these methods. For example, with static checkpoints, they aren't particularly memory efficient. So one thing which Alpaca took extra care to do was to help mitigate static checkpoints since they take up so much extra memory. And dynamic checkpoints are not as time efficient, so it causes things to run a bit slower if you're taking checkpoints dynamically. So next is task-based systems, and these help ensure that atomicity constraints are met. So essentially this is a method of keeping track of specific tasks. And two of the authors of this current paper, Colin and Lucia, both created Chain, which is what this picture is showing right here. This is an excerpt from their Chain paper, where it's essentially another task-based system. So I've already kind of hinted at it in these previous slides, but next I want to bring up where exactly does Alpaca fit into these? Does it have the same drawbacks as prior work? What does it do differently from the prior work? And how can we use this system to mitigate the issues brought up earlier? So in order to answer these questions, we need to look at what exactly is Alpaca. So Alpaca is a task-based programming system which uses privatization to do memory management. So a task, in this case, is a programming abstraction for preserving progress where each task is atomized. So in this case, as mentioned earlier, atomized is when a task only does one thing and sort of the rest of the program or the rest of the computing process assumes that it only performs that one task and it's not in the state of being in the middle of it. So this helps preserve different types of memory management. And privatization is essentially something I'll explain in depth a little bit later, but it sort of ensures that when different values change, they're entirely localized to the task. So this helps preserve the atomization since any kind of memory changes is exclusive to that task. So this is very similar to Chain, as mentioned earlier, but uses privatization. So that's like the main difference between this and Colin and Lucia's private work. So as you can see in this example, the flow of it sort of has a task, and this is sort of a new programming piece integrated into it, sort of similar to a function, where you have this task introduced, similar to a function call. An operation is performed within that task, and then it transitions to another task. So sort of like this task chain going on, similar to Chain mentioned earlier. And this is sort of used to perform, I sort of think of it like its own little mini checkpoint system, where each task sort of like takes the checkpoint after the task is completed in order to flow into the next task. So there are a couple of new lines and phrases used that the programmer needs to take into consideration when using Alpaca. So these are things that the programmer needs to actually like write into their code rather than just running it on a pre-existing program to transform it into an intermittent computing program. This has to be done by the programmer. So you can see here that they have a task, and this is atomized, as mentioned earlier, and each task has to lead to another task or termination. So we can't just have like a task in isolation, and we can't necessarily call a task and then another task right afterwards. It sort of like has to lead into the next one. You can't just have them all like execute like subsequently. Next, we also have transition 2, and this transfers the current task to a successor, creating a checkpoint as it does so. So this sort of like is the checkpoint system, but instead it's localized to an entire operation instead of just having an isolated checkpoint in the middle of a line of code. Next, there's entry, and this identifies a task which runs when the device boots for the first time. So this is sort of like a startup task. So when you're first setting up the device, this is what runs. This could potentially be like a ping to say, hey, the device is set up, or some other type of system. And then there's init, which executes first on every reboot. So this is commonly used to initialize hardware. So if you have a certain like thermometer, say, and you want to take a temperature, you sort of use init to initialize that thermometer before using it. And then there's also TS, which identifies variables which are shared between tasks. So if you have like a variable that's used for multiple different tasks, this is where you'll keep it, sort of similar to a global variable in a regular program with functions. And with a global pointer, that keeps track of the current task. So this is essentially sort of used to keep track of the current task and ensure that you aren't like accidentally getting mixed up between them. And the global pointer is in non-volatile memory to ensure that this pointer is preserved even when the power disappears. And keep in mind, the global pointer does not keep track of space inside the current task, since there is no internal checkpoint system for each task. Each task is isolated and atomized, as mentioned before. So the global pointer just keeps track of the task, not the contents within the task. Next, we have privatization, and here I'll explore the scalar method of privatization, but they also explore the array-focused privatization method in the paper as well. So essentially, task-shared variables are privatized. So remember before where we introduced TS, this variable is going to be privatized, so then within the program, it is exclusively changed in that program, and then it's updated once that task is concluded. And this ensures that everything is isolated in each task instead of being transferred between different tasks. So variables are stored in two places. A privatization buffer while the task is running. So as you can see here, we have this priv thing right here in this example. And then it's also preserved in the original location when the task is completed. So you can see it's pre-committed into this original C value right here. So basically we have like the privatization first while the task is running, and then we put it into the commit once it's done. So this sort of ensures that it's updated when we need it in the task, and then it's also updated outside of the task. And it essentially has a two-phase commit. So you can see here, in this example here, first we commit it, we add it to the commit list, we add A to the commit list in this example. Then we successfully commit it, and it's updated in the data, and then we sort of resume as usual, and we pre-commit B when we run the next operation. So this ensures that everything's always kept up to date only within the task. So there are a couple of conclusions we can make. It takes low overhead, which is explored a little bit more in the paper, since it uses selective privatization and only privatizes variables which are involved in write after read dependencies. The paper found that write after read dependencies causes most, if not all, of the potential non-volatile and volatile memory management issues. So only doing it selectively helps limit some of the issues, and this results in a lower overhead than Dino, which does not necessarily have this selective method. Next, we have memory consistency, since non-volatile memory and volatile memory maintain consistency, since write after read dependencies are taken care of, and there's this privatization method within the task, so when the task is interrupted, it's not updated throughout the entire program. Next, we also have input and output functions, which can also have issues when there's a power failure. So when taking measurement, but this can be mitigated by careful programming. So they explain this a little bit more in depth in the paper, but essentially there can be a couple of issues with input and output functions using this method. Since the programmer has to keep into consideration creating tasks and transferring from different tasks. So if they do it in a certain way, there can potentially be issues when using input and output functions. However, there are ways to mitigate this when using this method. Another issue is that another feature is that forward progress is reliant on the programmer, so they will need to create subtasks. So essentially, in this case, the programmer needs to be aware of what computation can be performed within the power constraints of the device. So when they essentially create their program, they sort of need to take that into consideration, and they can split up tasks pretty easily using that task chain system. And you can also see here that you can reuse tasks again and again, sort of similar to a function, in order to help preserve that forward progress. You can use this using a successor system. So it is possible to maintain forward progress, but it does rely a lot on the programmer. And this is unlike other prior work where checkpoints were sort of inserted in automatically. Next, there is a reusability of tasks, as mentioned before, where essentially you can use a successor system to reference other tasks. So that is the conclusion of the introduction to Alpaca. The paper has a little bit more detail on how it compares to the prior work, and it also has a bit more detail on specific benchmarks when compared to the prior work as well. So I think that this system is pretty useful in the intermittent computing space, and I think that it can be really useful for essentially having different task-based systems and preserving memory management really consistently. However, I do think it puts a lot of the onus on the programmer in order to make things work, which is pretty typical for most programming languages and just programming in general. But I think it does cause some limitations when they're compiling for different devices, since one device may have a more strict power constraint, and the programmer may not necessarily be programming with that device in mind, so it may provide a limitation in that case. But I think I was able to learn a lot about the prior work in intermittent computing by reading this paper, and it was pretty cool to learn about a new feature in the intermittent computing space.